Thank you, Andrew. So I'd like to thank the organizers for inviting me. It's always a good opportunity to come to Paris. So I'm going to talk about a very well-studied problem in statistics, a problem of density estimation. And just to connect my talk to Greg's talk, so the last part of Greg's talk, and I think the first one as well, which I missed, sorry, is the following, that we have some discrete distribution over some domain. Let's say the domain size is n, so a finite domain. And we want to learn it up to total variation distance epsilon. So epsilon is our desired accuracy. The question is how many samples do we need to do that? And what is, let's say, the best algorithm, the fastest algorithm? Now, generically, without any assumptions about the underlying probability distribution, the best thing you can do, like both upper and lower bound, is this. So you need linear dependence on the size of the domain and quadratic dependence on epsilon. This is pretty straightforward. You just take the empirical distribution after this many samples, and it will work. And information theoretically, you can prove that no algorithm with fewer than these samples is going to work for this problem. Now, this is well known. So in particular, this basic fact implies that if your underlying distribution is not discrete, but it's over a continuous domain, and you do not place any restrictions on its structure, the problem of learning under the total variation distance is just not solvable with a finite number of samples. Okay, so the next question is, okay, let's assume that the distribution that we're sampling from either exactly or approximately satisfies some structure. And now, can we exploit this structure to be able to solve the learning problem with fewer samples and more efficiently? So in time polynomial or ideally linear in the information theoretic minimum sample complexity. So the last thing that Greg talked about was that our discrete distribution is going to be, let's say, an n by n matrix. So it's going to have support n squared. Okay, so without any assumptions, we can do n squared divided by epsilon squared samples. But now the additional thing that we're going to assume is that this matrix is going to have rank 2. Okay, so this is, like the ijth entry is the probability that you take, the ijth element. Okay. Now, if the matrix has indeed rank 2, one can show that information theoretically order of n divided by epsilon squared samples are enough. But the natural information theoretic argument that gives this upper bound leads to an exponential time algorithm. So the running time of the underlying sort of information theoretic algorithm would be exponential in n. So it's not good. Okay, and I suppose, so is Greg here? Okay, he's not here yet. The point is that it's a very important problem to whether we can actually achieve this information theoretic minimum with an efficient algorithm. Okay, we can obviously get a polynomial time algorithm because we can just use the obvious bound. It's still going to be a polynomial time algorithm. But if we insist that our algorithm uses the information theoretic minimum, it's unclear whether such an algorithm, whether an efficient algorithm exists. Okay, and in fact, for this particular setting, it is possible. Now I'm going to talk about a related setting for one-dimensional probability density functions that have a certain structure, which I'm going to describe. So the broad context for the talk, I don't know what's the best place to stand, maybe here, so I'm interested in a complexity theory for statistical estimation, where the goal is to not only design estimators that achieve the information theoretic optimum, but they're also running polynomial time, and ideally linear time, nearly linear time. Polynomial is not good for many of the applications that we're interested in. So the challenge I'm focusing on is obtaining computationally efficient and robust estimators for fundamental inference tasks. So this is the general framework. And in particular, I'm going to talk about density estimation, or the problem of learning a probability distribution from samples, which is this problem. So we get independent samples from a distribution with density f. So I will assume for the entire talk that the distribution is defined on an ordered domain, let's say over the real line or over a discrete domain that has a partial order. And our goal is to output a distribution G which is a good approximation to f. To avoid misunderstanding, whenever I use letters for distributions, they're actually letters for the corresponding probability density functions, if they're continuous, or the probability mass functions if they're discrete. So this is the problem we want to solve. So this blue curve here is the true density. The only thing that we observe is independent samples. So this is what we see, these red points. And the goal is to actually reconstruct this, let's say, this blue curve. Now, this red curve is something that came out of our experiments. Now, how do we measure? So this is not well defined here. How do we measure the error? If you look at this picture, maybe you'll say, OK, this red curve doesn't look very much like the blue curve, right? So it has a bunch of spikes here. It's not exactly as beautiful. The error I'm going to focus on for the talk is a global error metric, which is going to be the total variation distance. Okay, even though the curves do not look identical, their L1 error is small. Okay. Now this is a very classical problem in statistics. It was introduced by Pearson in '94, and this is 1894. This is essentially the first problem that statisticians studied together. Actually, the second. The first one was hypothesis testing, again by Pearson. Now this is the statement. So fix an epsilon, which is our desired accuracy, L1 error accuracy. Let D be a family of distributions over the real line. We get sample access from some unknown distribution f that belongs to D. So this is a promise that f is actually from this family. And we want to output some hypothesis such that with high probability the L1 error between the hypothesis and the true distribution is at most epsilon. Okay, so this is the problem. Now, this is a little bit different as a formalism for most statisticians use. Statisticians usually have little n, which is the size of the sample, and see how the expected error of their estimator scales with n. For example, it might scale as 1 over square root of n or something like that. So this is basically equivalent. I have just changed the parameters, and I start from epsilon, which is the desired accuracy. What's the minimum sample size needed to achieve this accuracy? Does it make sense? OK. So one reason I'm going so slowly is because I understand that not everyone is from my community in this room. So I want to make sure that I'm not confusing people by not defining things properly. So and again, we're going to assume that our distribution comes from some structured family. And this is something that is both necessary and natural. So there's a long line of work in statistics. In fact, different branches of statistics study different versions of this problem. For example, like what is the family that we might consider, the family of distributions where the samples come from? Maybe it's, let's say, a mixture of Gaussians in one dimension, or something a little bit more general, a mixture of low-concave distributions. Or perhaps the underlying density has some smoothness assumptions. So this is something called the Bezov space in mathematical statistics. So there are many restrictions on the shape of the underlying probability function that people have studied historically. Now, one thing I'd like to point out is that our hypothesis, so what the estimator outputs, is not necessarily part of the family D. Okay? So the hypothesis that we output is not necessarily proper. Okay, so this is something that we call improper learning versus proper learning, where we actually insist that the output hypothesis is, in fact, a member of D. This is also an interesting problem, but this talk doesn't study this. Okay, so this is the problem. Now, our metric is the statistical distance, total variation distance, which I write like this for a reason that's going to become clear. So what is it? What is the L1 distance? It's like twice the supremum of f of a minus g of a for all measurable subsets. Okay, this is like the definition. It's actually very useful because of what we're going to do next. Okay. Now, what do we care about when we study learning algorithms? I mean, this is true essentially for every inference task, but in the context of learning distributions, one thing is the sample complexity. We want to be information theoretically optimal. Number two is the running time. So we really want the running time of the algorithm to be polynomial or ideally linear in the size of the sample. Number three, robustness. So what happens if our assumption that the density belongs to the family D is not actually satisfied exactly, but satisfied approximately. So if the model is misspecified, we want our algorithms to be competitive even in this case. And number 4, we want generic estimators. Okay, so ideally, if someone asks me for a density estimator for a mixture of Gaussians versus a mixture of exponentials versus a mixture of log concave distributions, I would ideally not like to design a specific estimator for each family, but have something generic that works as well for all of them. And this is something that we can achieve in this very specific setting. So the main result I'm going to describe is a meta-algorithm which achieves all these 4 goals for a very specific family of distributions in one dimension. So more specific, so what are the guarantees? So the algorithm is robust to model misspecification. It uses a sample size which is optimal up to at most logarithmic factors. And most importantly, the running time of the algorithm is nearly linear in the size of the sample. Okay, which means that basically we cannot improve on this by at most logarithmic factors. Okay, since the sample size is optimal and the running time of the algorithm is linear in the sample size, this is essentially the best that we can do. Now, to describe the framework, I need to define what the basic object of study is, and this is piecewise polynomial probability density functions. So the notation is going to be this. So we have t intervals at degree d, and p, calligraphic p of t comma d, is going to be the set of piecewise polynomial densities with t pieces and degree d. So we take our domain, we partition it into t intervals in any way we like, and within every interval, our distribution is going to be a polynomial of degree at most d, and everything again is still in one dimension. Now the problem statement is the following. So given the number of intervals, given the degree, and given samples from an arbitrary probability density function over the real line, our goal is to output a piecewise polynomial with the desired number of pieces and desired degrees, such that the total variation distance of our hypothesis from the true distribution that we sample is at most opt plus epsilon, where opt is the best, existentially, the best approximation of our unknown density by a piecewise polynomial with t pieces and degree d. Is the definition of the problem clear? Yes?
So I'm confused. The last piece on the is already a zero polynomial. What does it mean for density go to infinity?
OK, I see. So you can assume that instead of the domain being R, it's just a compact subset of the real line, let's say a finite interval. OK? So let's make f from, let's say, an interval AB, which is unknown, to the non-negative reals. OK?
I mean, you can always get a lot of sometimes that we can.
That's what I was asking. The int is always zero polynomial.
So what you can do is the following. So get samples. Let me address this very simple. So you can just first get samples from an arbitrary distribution over the real line and discover where the support is. Discover a finite interval that contains 1 minus epsilon over 2 fraction of the mass. You can do this with over epsilon square samples. And after that, you reduce it to the case of a compact support. So this is not a big problem. But like, to be formally correct, the actual domain is, let's say, a finite interval. Okay? So this is the problem statement. Now, I'm going to relax it a little bit as follows, that in fact, my hypothesis is going to have a little bit more intervals than t. It's going to have order of t intervals. And this is a useful relaxation. It's not a necessary relaxation. It's a useful relaxation for one of the things I'm going to do. This is the first relaxation. And the second one is that there is a constant factor approximation in front of the opt. So we don't achieve opt plus epsilon. We achieve c times opt plus epsilon, where c is a constant. And this is something like 3 in the results that we do. And in fact, some constant here is actually necessary. So if, let's say, with constant c less than 2, the problem is just not solvable. Okay? You need infinitely many samples. Now, so the right constant is something between 2 and 3, but this is not like a big deal, because for all the applications that I care about for this type of problem, I'm going to apply it for the case that opt is going to be small. Therefore, what the constant is doesn't really matter. OK. Now, given such an algorithm to learn piecewise polynomial density functions agnostically, I can use it to learn any structured family of distributions over the real line as follows. First, I approximate the family that I'm given. Let's say if the family is a mixture of log-concave distributions over the real line. I approximate it by piecewise polynomials, which means that I existentially determine what are good values for the number of pieces and the degree, such that the opt is going to be at most epsilon. Then I run my algorithm, the piecewise polynomial learning algorithm for these parameters t and d. I get some hypothesis and I output the hypothesis. So that's the algorithm. And it's pretty straightforward. It's going to work. So it's going to give you that the L1 distance to the truth is going to be order of epsilon. Okay? Is this clear? Now the question is, why do we do that? Like how did we come up with this choice of hypothesis class? So there is, so I come from TCS. So there is some analogy of this problem to pack learning of Boolean functions, where a very successful framework for learning Boolean functions in a large number of variables is by approximating by low-degree polynomials. Now, in statistics, fitting splines like low-degree piecewise polynomials to the data is a very well-studied approach. In fact, many people since the 80s have studied this problem, but in a somewhat different framework than ours. And the focus in that community is more about the statistical efficiency of the maximum likelihood estimator as opposed to getting computationally efficient algorithms. And the post hoc justification is that, in fact, this type of approach gives sample optimal and computationally efficient algorithms for many distribution families. So the main theorem, joined with Acharya, Lee, and Schmidt. So these are students at MIT, Jerry, Lee, and Ludwig Schmidt, and Jaddev is a postdoc at MIT. So this work was done 2 summers ago when I was visiting. Is that there exists an algorithm for this problem, for the problem of agnostically learning piecewise polynomials, that has the following guarantees. So the sample complexity of the algorithm is going to scale as follows. It's going to scale linearly with the number of pieces, linearly with the degree, and quadratically with the error. And the running time, and this is the most important part of the theorem, is going to in fact be nearly linear in the size of the sample. Okay, this is really the main algorithmic contribution of the work. In fact, the sample complexity bound follows very easily from information theoretic arguments, which I'm going to show. Now, previously, we had a paper with Chan, Servideo, and San a couple of years ago in Stock that solved the same problem, but had running time polynomial in the size of the sample. So this polynomial was something reasonable, but not practical. So the degree was something like 10 in some of the parameters, in particular in epsilon, and the degree, the dependence was actually pretty bad. The dependence on t was at least cubic, I think. And the second thing I want to say here is that, in fact, the sample complexity of this problem, independent of running time, scales like this. So information theoretically, to solve this problem, you need t times d plus 1 divided by epsilon square samples. So this is something that one can show using standard information theoretic tools. So as a corollary, this algorithm is essentially the best thing you can hope for in this setting. Now, as an application of this algorithm, we obtain, using the framework that I described, we obtain sample optimal and nearly million time estimators for learning various distribution families. And this is like some applications of what we can get. So now maybe I should move to the board for a little bit. So can you pick a row in this table? Greg? Okay, I'm going to like... Okay, I'm going to do the third one and the fourth one, okay? So, so a superset of what you selected. You selected the Gaussians, right? Okay, so what is a log-concave density? So we all know what a log-concave function is, right? So how do we learn such a function? By applying this framework. So the first thing we can try is approximate a log-concave function by a piecewise constant, okay, by a histogram. So what do we get? So basically, we constrain the degree to be 0. And the question is, how many pieces do you need? How many intervals do you need? So that every log-concave density on the real line is epsilon close to a piecewise constant function. And the answer here is that you need the t, the number of intervals, to be at least 1 over epsilon. So this is both an upper bound and a lower bound. So with 1 over epsilon pieces, you're good. So if you apply what I just said, so let me remind you that the generic sample complexity of the algorithm and the running time is something like that. You would get a sample size of 1 over epsilon to the power of 3. Okay, now from what you can see on the board, this is not optimal, right? You can infer it from what is written. And the reason it's not optimal is because if you actually use degree 1, so you approximate log concaves by piecewise linear functions, then you can do much better. You can approximate with 1 over square root of epsilon pieces. And this is what gives you the 1 over epsilon to the 5 over 2. Okay? Now, one can try to use higher degrees, but for this particular case, for the case of log concave indices, but believe me that if you do that, you will not get any savings. And you can independently prove that the problem of learning log concave distributions, in fact, information theoretically requires this many samples. Now, this bound is something that, in fact, can be obtained by taking the maximum likelihood estimator. What cannot be obtained by taking the maximum likelihood estimator is the row below that, which is the case that we have samples from a K mixture of log concave distribution. So the sample, so you have K log concave distribution, some mixture over them, and you take a sample. So the framework of piecewise polynomials immediately generalizes to the mixture case. Okay? In particular, the only thing that changes is that if I have a K mixture of things in the class, I would multiply the number of intervals by K. Okay, the degree is going to remain the same. The number of intervals is going to be multiplied by K, and I would get the sample complexity of K divided by epsilon over 5 over 2, which is actually optimal. Now, the important thing is not the sample here, is that in fact, the running time of the algorithm is going to be nearly linear in the size of the sample. So it's something, the best thing you can hope for. So that's it for this line. And let's go below to Gaussians. So Gaussians are log concave, as you all know. And therefore, whatever I've said about log concave applies to Gaussians. Can we do better? The answer is yes. How would we approximate a Gaussian by piecewise polynomials? The easiest way to do that, which in fact turns out to be the right way, let's just take a standard Gaussian. You throw away the tails. And for the middle part, we're going to use a Taylor polynomial of degree log 1 over epsilon. Okay, so this shows that if you use a piecewise polynomial with 3 pieces, 3 intervals, and the maximum degree of log 1 over epsilon, you can approximate every Gaussian with 0 epsilon. So this is the number of intervals. This is the degree, and the number of intervals is 3. Therefore, the bound we would get by applying the method is something like that. This is the sample complexity for a single Gaussian, and if you have a mixture of K Gaussians, you just multiply everything by K. And again, this bound is the best possible up to this logarithmic factor. In fact, just out of curiosity, is it clear to everyone how many samples do we actually need of information theoretically to solve the density estimation problem for a mixture of K Gaussians on the real line? Do we actually need this log or not? And you are not allowed to answer. Okay, so the answer is no, we don't need it. And the reason is that if you get 2 mixtures of K Gaussians, they intersect in at most order of K points. Okay, so if you have this property, then standard information theoretic arguments, some of which I'm going to mention, tell you that the actual sample complexity of the problem doesn't have a log here. On the other hand, we didn't know how to do anything non-trivial by even relaxing this by polylogarithmic factors before. If we actually want an efficient algorithm, it wasn't known how to do it with less than something like poly K over epsilon samples. So the contribution is that you can actually get a near optimal sample size with an efficient algorithm, with a fast algorithm. Okay, these are like 2 of the rows that of this table. So everything else is the same. It's like basically we apply the framework and we use the right approximation theory result. Now everything on this board is optimal up to polylogarithmic factors, at most polylogarithmic factors. Okay, that's it. Now, let me give you now some ideas of what we're doing. Andrew, how much time do you have?
You said 10 minutes late, so I guess not 25 minutes.
Okay, sounds good. So now I'm going to give you some ideas of how these things work. Now, what is learning? Learning is nothing more than optimization on the sample. So we get as input the sample, and we need to decide what our right optimization problem to solve is. We solve this optimization problem on input the sample. We output the hypothesis that we hope to be accurate. Now, the standard thing that statisticians have been doing in this context is, so what is the optimization problem they have been solving? For the most part, it has been the maximum likelihood estimator. So this is the optimization problem that you solve. You get the sample as input. You compute the hypothesis in your class that maximizes the likelihood of the data. Now, this has, this is very good, but it has problems. In particular, in this case, one can show that for many of those families, it doesn't satisfy any of the properties that we discussed. So it's not necessarily sample optimal. It might lead to an intractable optimization problem, and the robustness is not there, at least not under the total variation distance. So the first thing that we need to do is actually decide what optimization problem are we going to solve. And to do that, even though we desire to solve our problem over the total variation distance, we are going to define a different metric between distributions, which is going to help us decide that. So this metric is something that exists in statistics, and it's called, at least I call it, AK distance. And what it does, it actually tries to optimize over a smaller set than the total variation distance. I'm going to clarify this. So what is the L1 distance between distributions? So F and G are densities. So this is G, and this is F. So the L1 distance is this area. Okay? Now, one can rewrite this equivalently like this. Okay? What we do is that we partition our domain into any number of intervals. We see how much mass F and G assigned to those intervals, and when we sum the L1 distance between the reduced distributions, and we take the supremum over all possible partitions of the domain into our intervals. Is this alternate definition of L1 clear? Do you believe it? Okay, it's clear, okay? Now, I mean, this is trivial, okay? Now, the point is that if we generalize a little bit, it gives us something useful. Now, what I'm going to do is that instead of partitioning my domain into an arbitrary number of intervals, I'm going to partition it into k intervals, where k is a parameter. And I'm going to do the exact same thing. So I'm going to take the sum from I equals 1 to k of the absolute value of the L1 distances over those intervals. And I'm going to take the supremum over all partitions of the domain into k intervals. So this is something that's called AK distance. It exists in statistics. I did not define it myself. Maybe it doesn't have this name. And the main intuition is that what it tries to do is it tries to account for the k most important crossings between the densities F and G. So in particular, suppose you have a family D of distributions that you want to learn, and there exist two families, two distributions, F and G in the family, that look like this. Do you see this? You can see that the number of crossings between these densities can become arbitrarily high. You can see that you can have a bunch of crossings here. But really, their contribution to the L1 distance is very small. So the point is that when you are in a situation like this, you only need to consider the important crossings. And the important crossings is something that one can determine on a case-by-case basis for the given family. Okay, so some straightforward fact is that the L1 distance is always bigger than the AK distance. In fact, the limit when k goes to infinity is the L1 distance. And also the AK distance at most k times the value for k equals 1. Now, and the main fact we're using here, the sort of straightforward fact, is that in fact, the AK, yes? Okay, because I didn't define it properly. So this thing here is not necessarily a partition. We just take k disjoint intervals of the domain. Okay, so when it's not necessarily a partition, it's not. Yeah, thanks. That's a good point. But you're paying attention, which is good. Okay. Okay. So now the point, the basic fact that we use is that if you have two density functions that cross at most k times, the L1 distance between them is equal to the AK distance between them. This is just a corollary of the definition. And as a consequence of that, if you have two T piecewise degree D polynomial, they cross at most this many times. Therefore, their L1 distance is equal to their A2T D plus 1 distance, which means that to learn such a function under L1, it just suffices to learn such a function under this metric. And this is the thing I'm going to use. Now, the second tool I'm going to use is a basic information theoretic fact, a basic information theoretic inequality, which is called VC inequality. It's true very generally. It says that for an arbitrary density on the real line, if you take the empirical distribution after n samples, then with high probability, the AK distance between the truth and the empirical after n samples is going to be order of square root of k over n. Okay, so the empirical is going to be close to the truth, but of course not in L1. For example, consider the case that f is continuous, the empirical is discrete, the L1 distance is going to be 1. But in this metric that takes the supremum over all unions of at most k intervals, this distance is going to be close, and this is like a uniform bounds. So which implies, okay, that, okay, so this is a non-trivial theorem to prove, but it's like very well known. So this implies that how many samples do you need to learn under this metric? You need k divided by epsilon square samples. But still, so the empirical is going to be your correct hypothesis. But on the other hand, the empirical is not very useful because it gives us nothing under L1. So what are we going to do to learn? I'm going to give you an algorithm which basically establishes an information theoretic upper bound. This algorithm is going to be computationally inefficient. So it shows you that like a certain number of samples suffices. And the main contribution is actually turning this algorithm into a computationally efficient algorithm. And most likely, I won't have time to go into this. But at least I'm going to give you some high-level ideas. So the theorem says that there exists a computationally inefficient algorithm for learning T piecewise degree D polynomials within epsilon that uses this many samples. This is what I claimed in the beginning. And the way to prove this, like one way to prove this, is by using this AK distance combined with the VC inequality. So what do? We take our samples that form the empirical. The empirical now is going to be our inputs after we take our samples. And what we do is we output a hypothesis H, which is a degree, a T piecewise degree D polynomial that minimizes the AK distance from the empirical, where K is this quantity. So this is the optimization problem that we need to solve. If we can solve this, then we're good. Do you see why this algorithm works? Okay, so let me explain why. So now the truth, the function f that I'm trying to learn is not necessarily a piecewise polynomial, but there exists a piecewise polynomial p star which is at distance opt. That's the assumption. Opt is something between 0 and 1. It's unknown to the algorithm, and the goal is to be competitive against this quantity. So what do? We want to bound the L1 distance between H, which is the hypothesis that we output, is this quantity, the minimizer of this optimization problem, and F, which is the truth. So we use a triangle inequality first for the L1 distance, where in the middle we have P star. P star is the closest piecewise polynomial to our function. Okay? Now out of these two terms, one of them is easy to bound. It's the second one. The second one, by definition, is opt. And the first one, note that since P star is by definition a piecewise polynomial, and H is by definition a piecewise polynomial, the L1 distance is equal to the AK distance for this value of K. So now it suffices to bound from above this first term. And again, H is my hypothesis, and P star is the closest piecewise polynomial to the truth, which I do not know. How am I going to bound this? So it boils down to doing a sort of a combination of triangle inequalities plus using a VC inequality and the definition of the hypothesis, which I'm going to do. So what do I do here? First of all, I use the triangle inequality. So the AK distance is a metric. So I can bound this by the sum of the AK distance between H and the empirical and P star. Okay? So this is what I have now. So what now? Note that out of these two terms, the first one is bounded from above by the second one. Why is that? By the definition of the hypothesis H is the piecewise polynomial that minimizes quantity. P star is a piecewise polynomial. Therefore, this distance at most this distance. So really what I want to do is bound the second term. So how do I bound this term? I use a triangle called the again, where I put f in the middle. F is the true density that I'm looking for. So now I have the AK distance between P star and f, plus the AK distance between f and f hats. So what is the first term? How can I bound it? So note that this AK distance between any two functions is at most the L1 distance. And I know that the L1 distance between P star and f is opt by definition. Okay? So, and the second term is just the AK distance between f and the empirical. And by the VC inequality, since I took enough samples, this is going to be at most epsilon. Therefore, the second term is going to be at most O plus epsilon. So in conclusion, I'm done. Okay? So this optimization problem actually does the work. It achieves the optimal sample size up to a constant factor. The issue is that it's a non-convex problem, and it's unclear how to solve it. And the main contribution of what we did is to design a polynomial time algorithm for this problem. Are there any questions so far? OK, so let me give you some overview of the algorithm and a little bit, perhaps, the analysis for the case of histograms. So there are two parts of the algorithm. So CDSS here is the first paper that got the first polynomial time algorithm for the problem. And ADLS is the new paper that got the linear time algorithm. So there are two main ingredients. Okay? The first thing you need to do, since you're trying to fit piecewise polynomials, is to, in some sense, discover what the right partition into intervals is. Okay? So this is something that the first paper did by using some kind of dynamic programming, which is slow. And in my opinion, the most interesting contribution of the second paper is in fact that we can replace the dynamic program in this case by an iterative greedy algorithm that runs in linear time, so linear in the number of pieces. And the second ingredient is to actually, given an interval, to fit the best low-degree polynomial, degree D polynomial, to this interval. So this turns out to be a convex optimization problem, which you can solve. Now again, if you use soft approaches to solve it, the running time you're going to get is not very good. So this is what we did in the first work. And the second work, so yeah, again, this here is obviously a typo, right? So this is not a greedy algorithm. This is some kind of linear time separation oracle that actually gives you a running time which is nearly linear in the optimal sample size. Okay? Now, in the remaining time, this is like about 10 minutes. Okay, I'm going to give you a quick idea of the iterative greedy algorithm for the case of histograms. So you want to fit a piecewise constant function to your data. So what do? For simplistic, we work over minus 1, 1. So a k histogram is just a k piecewise polynomial with degree 0. So it's something like that. And what we're going to do is use a flattening operation. So basically, given a distribution f and an interval I, the flattening of f on I is just the constant function, which is equal to the uniform subdistribution of that interval. So for example, this is like a 3-flat distribution. Okay? And now, given a partition of a domain into a number of intervals, we consider the flattening of the distribution with respect to that partition, which is the obvious thing. Now, the algorithm is very simple. Its analysis is somewhat involved. So what we do, we take our samples, we form the empirical. Then we start by a partition which has basically one interval for every sample. And then for every 2 consecutive samples, you have another interval that contains 0 samples. So this is the initial partition that we form. This partition is big. It has many, many intervals. And what we're trying to do is merge iteratively consecutive pairs of intervals and somehow hope that this merging operation is not going to increase the distance from the truth. So what we do is that, so what's the number of initial intervals? Is something like 2n, okay? Twice the number of samples. Okay? So what do? We take our let's say, initial partition, we consider pairs of consecutive intervals, and we compute some quantity of error, which I'm going to define what it is, for every such pair. Now, we order the errors. The 2k largest errors are not merged, and the rest of the pairs are merged. And we do this iteratively until we remain with, let's say, 4k intervals. So this is the algorithm. Okay, that's it. Now, the error for a given interval is basically the A1 distance between the empirical distribution on that interval and its flattening. Okay, so you can see that basically this A1 distance is actually useful not only for the information theoretic argument, but also for the algorithm itself. Okay, is the algorithm clear? Okay, so let's make some observations about this. So why is this a fast algorithm? First of all, whether it works or not is another issue, whether it actually achieves small error. Why does it run in nearly linear time in the size of the sample? So we start with a number of intervals with something like 2n, where n is the sample size. And essentially, in every iteration, the number of intervals that we have, the partition into intervals, goes down by a constant factor. And we stop when the number of intervals becomes like 4k. So now you can show that the running time of a single iteration is linear. So really, the running time of the algorithm is something like n log 1 over epsilon. Okay, so this is what the following slide says. I guess this is an illustration of the algorithm. So this is the running time of the algorithm. It's basically what I said. Now, of course, the main question is, why does the algorithm work? Why does it actually guarantee small error? So this is the theorem. Okay, this algorithm outputs a 4k histogram, such that with high probability, the error between the truth and the hypothesis is going to be at most 5 times opt plus epsilon. Now, another interesting characteristic of this algorithm is that the only thing that it does, like in terms of probabilistic things, it first conditions on the VC inequality in the beginning, and this is the only high probability statement that we need. After that, the analysis is completely deterministic. So basically what we're going to do is we're going to look at the final partition that the algorithm outputs. It's going to be a partition of the domain into 4k intervals. We're going to partition our intervals into intervals that contain a jump of the optimal approximation and do not contain a jump of the optimal approximation. And each one of the two we're going to bounce using some structural arguments that we establish. I don't think I'm going to actually go through this because it's like a little bit too detailed. Instead, I'm going to spend the last few minutes actually giving you a context. Okay, so this is the summary. Okay, this is what we do. We have the iterative greedy algorithm to actually. Oh, by the way, right, this algorithm was for the case that we have piecewise constants. An immediate generalization of the algorithm actually works for piecewise polynomials. The only routine that you need is a routine to obtain the best fit polynomial within an interval. If you have this, then you can use an immediate generalization of that as a black box to solve the piecewise polynomial case. Now, in terms of concrete open problems, okay, so like obviously in terms of like statistics, statisticians really like proper learning algorithms. They really want that their hypotheses are actually part of the class that we're trying to approximate. So if you're learning a log-concave distribution, you'd better actually output a log-concave distribution, because in many cases, we actually use those hypotheses for other tasks after the learning process. This is something that we can do, okay? But now it cannot be generic. It has to be something that uses properties of the underlying family. For example, for log-concave distributions, we can actually do that. We can, in fact, post-process the hypothesis that this algorithm outputs and computationally efficiently construct a log-concave distribution. So this is something that can be done. In terms of the underlying algorithmic ideas, there are various other problems where these ideas have been applied so far. One of them is in some specialized stylized version of regression, which is called segmented linear regression, where again, the best algorithm known for the problem before us was some kind of dynamic programming. And the iterative merging greedy algorithm that we have actually applies to that setting with some non-trivial modifications. So we can actually obtain linear time algorithms for this problem as well. And there are other hypothesis testing tasks, like say testing whether two distributions are the same versus far from each other, where the same framework can actually give big improvements. And in terms of broad context, so what did I do? I took a very special problem, so one-dimensional density estimation, and I gave you an algorithm that gives us everything we want. So sample optimality, computational efficiency, and robustness, and some kind of generality. We would like to do that in high dimensions. For the cases where at least it's information theoretically possible, because in many cases it's not. This is a big open problem. So robust estimators for high-dimensional problems are not known, and there is no reason to believe that they don't exist. In terms of other resources, like people lately have been interested in additional resources, additional to the ones I've mentioned already. For example, when you learn a hypothesis, you don't want to actually reveal information about the participants. Okay, so this is privacy. Or maybe our samples are partitioned into various processors. And what we want to look at is the trade-off between, let's say, the sample size and the communication to be able to solve the inference task. So these are open problems, even in this basic context. And the last one, which is something that I alluded to in the beginning, is that I actually gave you a setting where it is possible to achieve sample optimality with an efficient algorithm. So this is not always the case. One can construct artificial problems where there are inherent trade-offs between the sample complexity and the computational complexity. In particular, you can show that under plausible complexity theoretic assumptions, no algorithm can achieve the information theoretic optimum and at the same time run in polynomial time. However, in this context at least, the only problems that I know that have this property are artificial. So the question is if there are actually natural density estimation problems for natural, let's say, high-dimensional distribution families where such trade-offs are actually inherent. And at this point, I think I'm going to conclude.